Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to cover the elimination reactions. Now, up to this point we've been focusing on substitution, and we've learned about the SN1 and the SN2 reaction. Well, just like substitution, there's an E1 and an E2 reaction. So it's very similar in the sense of whether the kinetics is related from E1 to SN1 or E2 with SN2. They have very similar kinetic ideas. Okay, so we're going to see that in just a moment. So we're going to keep with the same pace that we did where SN2 was a little bit slow, right? It took about an hour and a half and then problem solving over 2 hours to do that. But then we went a little faster with SN1. The same thing here. We're going to start with E2. It's going to take us a little bit of time, maybe not as long as SN2, but a little bit of time, maybe like an hour and a half. And then E1 is going to be very quick. After we do E1 and E2, we're then going to wrap everything up. We're going to talk about SN1, SN2, E1, E2 all together and figure out what makes them unique, how do you figure out what reactions taking place. We're going to do all that wrap up at the end. Okay, so our goal for this video is to focus in on E2. But I'm going to start with a quick introduction like I did with substitution. Okay, so as you can see from my list here, everything is exactly as it was with SN2 and SN1. We talk about the mechanism, the kinetics, we go through the factors that make it faster, and then we wrapped up with some problems. That's what we're doing here, okay? Same kind of pattern. So the first thing I want to talk about, as I mentioned, is an introduction to this concept. Well, one of the first things that we have to recognize is that elimination requires not a nucleophile, it requires a base. Okay, so SN2 and SN1, they can have nucleophile or base, but for elimination, it's only going to be a base. So that leads to the obvious question, what's a base, right? What makes the difference, not what's a base, but what makes a difference between a nucleophile and a base, right? So that's what we're going to do right here. First I want to point out is that all bases are nucleophiles, all of them. So remember that a nucleophile is a kinetic concept. It's about pushing the rate of that reaction, making it faster. It's a kinetic idea, but base is a thermodynamic idea. Base is about stability, whereas kinetics, nucleophilicity is about kinetics, speed. Okay, so all bases have the fundamental requirement to be a nucleophile, and that is a lone pair. As long as you have a lone pair, you can be a nucleophile. Okay, whether you're faster or slower, that's the things we learned in SN2, right? But all bases are nucleophiles, but not all nucleophiles are bases, right? Are base. So you can't think of every nucleophile as a base because some of them are not. Like for example, I know that if I have an I minus, that's a nucleophile. So is, for example, Br minus. These are good nucleophiles. They're going to go in and they're going to do their job. As a matter of fact, I is really good under protic conditions, right? And so is Br. The bigger the better in the protic environment. But these are not bases, right? HI, HBr are very strong acids, so their conjugate base is very weak. So we would never think of these as bases. They're good nucleophiles, but not a base, right? The same thing with like a carboxylic acid. When we look at a carboxylate, we would never think of it as a base. We would think of it as an acid, right? And Cn minus, HCN is a good acid. It's a weak conjugate base. Okay, so these are examples of things that are not considered basic. Now, of course, then you have a lot of things that are basic, right? So, for example, we can have hydroxide. So, hydroxide is both a base and a nucleophile, whereas these are only nucleophiles, right? So, I'm giving you a list of both, I guess. So, let's do that. Let me erase that. Okay, so these are only nucleophiles, and these are just an example. There's many more, but you could have RO minus, NH2, H minus. These are very powerful bases, and we'll go into the logic of this. You don't have to worry about that right now because that's the next section. But these are examples of things that are both nucleophilic philes and also bases. So they're nucleophilic is what I was trying to say, and also basic. Okay, so some things you have to focus in on and determine, is it a base? And we're going to get a trend down in the next section, so don't worry too much about that. We'll see that in just a moment. It really comes down to looking at the pKa chart, and we'll do that soon. Now, what about this idea? What is elimination in comparison to substitution? Well, imagine if we have an ethyl bromide, okay? And this ethyl bromide can, well, actually, let's make it secondary. This ethyl bromide can react with either something up above, but that wouldn't allow us to explore elimination because the top stuff is only nucleophilic. They only do SN2 or SN1, right? So what if we look at something down here, like let's say CH3O minus, RO minus? Well, for SN1 or SN2, I'll write SN so we don't care if it's 1 or 2. In this case, it would actually be 2, right? You should know that because it's a secondary alkyl halide and a negative nucleophile makes it SN2 favored. If it was neutral, if this was OH, SN1 is favored. Neutral, SN1, negative, SN2. But let's just keep it negative so we can focus in on the base character. So here's a SN reaction, right? Which means that we're going to take the Br out and put in an OCH3 plus Br minus. But now another thing that can happen is we can go through elimination, E, with the same exact reagent because it's a base and a nucleophile. So how would that work? Well, what happens is if you think back from SN2 theory, I described the idea of an alpha carbon. An alpha carbon is the carbon that holds your point of reference. For this chapter, it's a halogen or a leaving group like OTOS. But in general, it usually is the carbon that holds the functional group, like an alcohol or an amine or a carbonyl group. Those are the alpha carbons. And next to them are beta. So if this is alpha and this is beta and beta, what this base can do, see right now we're going to use it in the terms of a base, not a nucleophile, but what this base can do is it can pull off an H from the beta carbon. And then that electron pair that the H once had can go and push out the Br, or it can go towards the carbon that has the Br. So, for example, we can have an H removed and then a double bond form and the Br leave, right? And so we would wind up with an alkene because now the carbon that was alpha, let's say here's the alpha, here's the beta, the carbon that's alpha has now got a double bond. It no longer has that Br. So we have plus Br minus, and we also have alcohol. We have plus CH3OH. So these are the things that we just made. Now the key here is that it's a question of timing, just like SN1, SN2. Does the Br leave first and then the base pull off the H? That's E1. Or does the Br leave while the H is pulled off and the double bond forms? That's E2. So remember SN2, just like that. SN2, everything happened at the same time. SN1, things happen at separate times. Same thing here with E1 and E2. Okay, so that's what we're seeing here. And this is an elimination reaction. It's all about the beta carbon losing an H, making a double bond to the alpha carbon, and the halogen or whatever the leaving group leaving. That's what it is. Okay, so this video is about E2. Like I had mentioned in the introduction. So we're going to focus all our attention on E2. We're going to learn a lot, and then we'll roll into E1 after some problems. Okay, so let's get started now and go through that traditional path of kinetics, the reaction with the energy diagram, and the factors that make a better E2 reaction. Okay, so let's do that here. And so just like with SN2, E2 is a concerted reaction. And so whenever things are concerted, that means that you're always going to have more than one dependency on the rate because everything has to happen at the same time, just like SN2. So our rate is equal to the rate constant times the substrate concentration and the base. Okay, actually I'm going to write A minus. That's the common way to write base. So substrate and base, which what that means is that if we have an elimination reaction and we double the substrate, we double the rate of the reaction, just like SN2 or even SN1. Think about it. They all depend on substrate. The question is, do they depend on the other part, the nucleophile, or in our case, the base? Well, in this case, it does. So if you double the base, you double the rate. If you double both of them, you quadruple.